Consider this curve in three-dimensional space. This is a 3D curve. In this video, what I want to talk about is line integrals over curves like this. In the previous videos on line integrals, my curves that I was talking about were always two-dimensional, but now I have a three-dimensional curve, and that's going to change how I interpret the concept of a line integral. So first of all, let me try to describe this R of t by a parameterization. So generically, my R of t is going to be some function g of t in the I hat, some function h of t in the j hat, and some function k of t in the k hat. And a parameterization also has to come with some restriction on the t. In this case, a generic restriction t is on some interval a up to b. Now, this specific example is a very important one. It's a helix. And so I'll actually put up what the functions g, h, and k are in this specific example. It's cos t, sine t, and then just t in the k hat direction. On the interval 0 to 2 pi gives you one loop of this helix. So this is a particularly nice curve that has this nice parameterization, but we'll just talk generally for most of this video. Now, above this curve, I want to imagine that I have some function of x, y, and z, where if x, y, and z are described to be above this curve, I can put them f of g of t, h of t, and k of t. Now, there's an issue. I can't easily draw this function above this curve because I've run out of dimensions. When I first introduced line integrals and my curves were just down in the plane, my function could be some height above the plane. But now that my curves are three-dimensional, I don't know where to draw my function. There's some tricks. Maybe you could use different colors to introduce different heights as you go along the curve, or maybe different thicknesses of the curve to associate different types of heights, if you will, above this curve. But in general, in 4 dimensions, which is what we would need if we have a function that's got a 3-dimensional input and a 1-dimensional output, it's hard to draw things. But that's okay, because the same basic idea of a line integral is going to apply. So what was our formula before? This is what we saw in the 2D case. It was the curve down in the domain, and then the function was above it. And then we had this formula that said the line integral of the curve, and we got some expression. Well, the 3D case is basically exactly the same thing. The only thing that's changed here is that everywhere I've added a third component. It's now f of g of t and h of t, and this new thing, k of t, and likewise, there's a k prime of t on my right-hand side as well. And I really do think of it as having this curve in 3D space, and then the function is above it. Okay, so it clearly doesn't represent the surface area like it did in 2D, but what might this line integral represent? Well, there's several different things it could do. First, imagine that this line is a wire, and everywhere along the wire, it's got a certain, what we'll call, linear mass density. So maybe every centimeter, say, of the wire has a different density, maybe made of different materials, or perhaps it's a little bit thicker in some spots than other spots. Either way, different linear densities. Then what the line integral represents is just the mass of that wire. The way to think about this is the stuff in orange, the square root of the g prime squared plus the h prime squared plus the k prime squared dt, all of that represented a little arc length, a little ds of arc length. So what I'm imagining is if I have my larger curve and I take some little section, some small little change in arc length, then what is the mass of that little section? It's just the density at that section times its arc length. And so you add up all of those little segments and you get the mass. So the line integral can tell you what the mass of a variable density wire is. Okay, let's see another example. Imagine this time you have a pipe, and your function f of x, y, and z represents a different width of the pipe as you go along the curve. So maybe at some spots the pipe is narrower, and some spots it's a little bit bigger. Then if I'm interested in figuring out, well, what is the total volume of water, say, in this pipe? Well then, it's again a line integral where your function here now represents that cross-sectional area. The way I think about this is, again, if I take a little unit of arc length, well then the volume represented by that change in arc length is just the area that I have at that spot, this a of t, times the little infinitesimal distance of arc length. Add all those up and you get the total volume. Okay, I'll give a third example here. This time my function is very simple. My function is just the function 1. And then if I plug this in, you get a formula that might be familiar from multivariable calculus. This was our arc length formula that you computed before. And it makes sense because you're basically just taking the arc length thing, the square root of all that stuff, and then multiplying it by 1, so of course you just get out the arc length again. And so it's a bit silly, but I can interpret line integrals as sort of a generalization of the arc length formula we've seen back in multivariable calculus. And then the final example we're not going to do in this video, but we're going to do it a lot as we go later on into vector calculus, because we're going to talk about curves going through vector fields, like, for example, the vector field that's created by gravity or the electromagnetic force. And we're going to see a ton of examples about line integrals in that context. But all of that is going to be in a later video.